Alrighty, welcome to the history of the atom, part 2. And in the last video, we discussed Dalton's theory of the atom and the 4 rules or tenets within that theory. Before we look at the experiments which helped elucidate the structure of the atom we know today, I want to take a quick, closer look at Dalton's theory. And so for Dalton, he knew, or at least he thought, that all matter was composed of these little packages of mass called atoms. But he didn't really know much beyond that. He knew that an atom from element A was very different, had a different weight, had different chemical properties than element B, but he didn't know anything about the structure of the atom, the internal structure of the atom. In fact, he thought that the atom was indivisible. But scientists and researchers around, 1900, the turn of the 20th century, began taking a closer look at the atom and tried to discover the secrets it had to tell. And the first of these was J.J. Thompson, doing work between 1898 and 1903, and his most famous experiment is known as the cathode ray tube experiment, and you'll see in a second. This here is a cathode ray tube, the eponymous cathode ray tube, and Thompson didn't actually invent this apparatus. It had been around for 20 to 30 years before this experiment, but he was able to use it to find or to discover some pretty interesting things about the atom. So the first we'll do a little bit of anatomy. This end of the cathode ray tube is called the cathode, and it was constructed Thompson used a lot of different metals. He ran this test a lot of different times using different kinds of metals, anything from aluminum, bronze, copper. He tried a lot of different things. And this end is the observational end. It's where you can see what comes out of the cathode, and what does come out of the cathode when an electric field is applied across this tube. We see a positive charge here, a negative charge here, are these rays of stuff. No one really knew what they were, but whenever an electric field was applied to the tube, these cool bright rays were seen to traverse from the cathode to the positively charged anode. What Thompson did was the following. He added these plates to the middle of his tube. The plate on top was given a negative charge, while the plate on the bottom was given a positive charge. And then Dalton reran an electric current through the tube to generate these rays. And what he found was actually very interesting. Rather than seeing these nice straight lines, which all the other researchers had seen when they applied electric fields to their cathode ray tubes, Dalton saw rays which did something like this. They would go straight for a while, and then bend away from this negatively charged plate as soon as they encountered that region. And they did this with some consistency. And so what did Thompson conclude? Well, at this point, researchers knew that the atom was electrically neutral. But these things, because they were being deflected from the negative plate and attracted to the positively charged plate, were clearly negative. They were clearly negatively charged particles. And because Thompson ran this experiment with a lot of different kinds of metals, a lot of different substances, he concluded that all atoms contained these strange negative particles. And so his first conclusion was that all matter contained these strange negative particles, which he called electrons. So all matter contains electrons. Okay, that's well and good. But at the same time, because the atom is electrically neutral, there must be some positive charge. There must be some positive charge in the atom to balance out the negative charge of the electron. And this led to the development of what's called the plum pudding model of the atom. It's sometimes called Thompson's model. And the reason it's called the plum pudding model, maybe I'll sketch it for you first. The plum pudding model looks something like this. This is our atom. Electrons are distributed within it like little raisins, like that. And then the positive stuff to counteract the negative charge of the electrons, is just sort of the space everywhere else. Thompson called this a positive charge cloud. Positive charge cloud. And the reason it's called the plum pudding model is because there's an English dessert, which I highly recommend, which sort of looks like this, and the electrons are raisins, and the positive charge cloud is this nice spongy bread-like substance. So positive charge cloud, and then these electrons are like raisins. I was about to write raisins. These are electrons. And so this was Thompson's way of accounting for the negative charge of the electrons, was creating this positive charge cloud. And so this was Thompson's model of the atom. And the last thing he did, the last conclusion he drew, was to calculate the charge to mass ratio. So Q is the symbol we use for charge, obviously M is the symbol for mass, of an electron. And he calculated this as negative 1.76 times 10 to the 8th coulombs per gram. And there are a few things we can take away from this number. First, we know mass is not negative, so the charge must be negative. And secondly, there's a heck of a lot more charge. Look at that number, 10 to the 8. There's a heck of a lot more charge than there is mass. So these electrons are very tiny things. And this number is nice to have, it's useful, but it would be really cool if we could determine the actual charge and the actual mass of the electron. And that's where this guy Millikan comes in, and with his oil drop experiment. And this is potentially my favorite experiment of the bunch. It's really cool. What Millikan did, he had a pretty simple setup. There's one box here, another box here, and a couple holes. This hole here, inserted into it, was an oil droplet dispenser. So these are oil droplets in this little dispenser, and they weren't just ordinary oil droplets, they were actually ionized. They were given a negative electrical charge, but they were extremely, extremely small, and so the charge on them was the result of only a few extra electrons. So only a few extra electrons were making these little droplets which are circulating in this box nice and negative. And then a few drops would come through this tiny, tiny, tiny hole here and enter this second box. And of course they're being pulled down by the force of gravity because these things have mass. Millikan applied an electric charge, or electric current, producing an electric field across this box such that the top was positive and the bottom was negative. Now remember that these oil droplets are negatively charged, so they're actually going to be pulled towards the positive plate. And because the force of gravity was pulling down, maybe if you've taken physics, you can analyze it like this. You've got your droplet here, negatively charged in blue. The force of gravity is pulling down. There's an electrostatic force pushing up. This droplet is actually going to be suspended, or it's going to move very, very slowly because of these counteracting forces. And because Millikan could sit there and record the very, very small speeds of these droplets, he was actually able to measure the magnitude of a charge on an electron, giving these droplets a net negative charge. Because Thompson had figured out this charge to mass ratio, and because Millikan had figured out the charge, Millikan could then use this number to figure out the actual mass of an electron. So he calculated the charge of an electron, as negative 1.6 times 10 to the negative 19, it's a very small number, coulombs, and then the mass of an electron is an even smaller number. As we've seen in previous videos, it's 9.11 times 10 to the negative 31 kilograms. And these numbers are extremely, extremely useful. We still use them today in all kinds of calculations. But we're still stuck with this plum pudding model, with Thompson's model of the atom. It was the accepted model of the atom at that time period up until about 1915, 1920. So a guy by the name of Ernest Rutherford, one of my favorite names in science, wanted to test this plum pudding model. He wanted to see if Thompson's model was accurate. And to do so, he ran his famous gold foil experiment. And this is another cool one. What he did was he took an alpha particle emitter. Now let's just take a look at what alpha particles are. Alpha particles are really just helium nuclei. They're composed of 2 protons and 2 neutrons. So they have a net positive charge of +2. And this emitter would shoot these high velocity alpha particles and give them a lot of energy, and they would shoot them towards this gold foil, this sheet of gold only a few atoms thick, so extremely, extremely thin, and these alpha particles would shoot towards this gold foil like that. And what did Rutherford expect? Well, he expected most of the alpha particles, really, he expected all of the alpha particles to go straight through. Because these had so much energy, they were moving so fast, and the gold was extremely, extremely thin, he thought all the atoms would head straight through and hit the back of his detector right there. What he actually saw was this. He saw quite a few of the alpha particles go straight through. In fact, the vast majority went straight through, but a few went off at angles like that, and like that, and like that. And a very small number actually, came straight back and almost hit the detector. And what does this mean? Well, if the plum pudding model of the atom was accurate, maybe we can just sketch what it would look like. The atoms in the gold would look like this. They would be here, they would have all their positive charge cloud, they would be arrayed like this, the mass would be evenly distributed throughout the atom, and the high velocity alpha particles should shoot straight through. They should go straight through, as Rutherford said, like cannonballs through gauze. The alpha particles have way too much energy to be reflected by these plum pudding atoms. But that's not what we saw. The way Rutherford reconciled his results with the current atomic knowledge of the day was to propose a new model of the atom, and his model was known as the nuclear model, and was something like this. Rather than having all the mass of the atom sort of splayed in this positive charge cloud, he proposed that almost all of the atom's mass, as well as its positive charge, was concentrated in the center in a really, really small region called the nucleus. Of course, these are not drawn to scale. They're way smaller than that. And this is really cool because it explains this refraction pattern, explains this deflection pattern, which Rutherford observed in his gold foil experiment. If we maybe blow up one of these nuclear atoms, we've seen them before, look like this, this is what Rutherford thought, a densely packed nucleus of positive charge in the center with electrons moving around the nucleus. He didn't know how they moved around the nucleus, but he knew that they did. This explains why, well, most of the alpha particles went straight through, because they would hit places like here and here and here and experience no force on them. They would just go straight through. However, when some alpha particles maybe experienced a near impact with the nucleus, they went here and here, they were deflected. We know the alpha particles have a positive charge. Remember that they're just 2 protons and 2 neutrons. Of course, the nucleus has a positive charge because of all the protons. We know that now. Whenever they came close to the nucleus, the alpha particles, they would swerve off like that and swerve off like that because of the repulsion between the positive charges. And that's why we see a lot of alpha particles being deflected from that straight line. They're being deflected to hit sides of the detector. And when some alpha particles had a direct hit with the nucleus, they would be reflected right back at the alpha particle emitter. And so Rutherford thought that this nuclear model of the atom helped explain his experimental results. And just to recap, Rutherford's conclusions were that 1, the nucleus was a densely packed region of positive charge and mass. We know that's true today. Of course, Rutherford didn't really know about neutrons, but now we know about protons, and those protons constitute the positive charge which Rutherford was talking about. Also, if we look at this model of the atom, most of it is nothing. There's really not a lot there. And so 99.9, we'll say 99% of the atom is empty space. And that was one of the real shocking results of Rutherford's experiment. How could the wood I'm hitting right now, how can the computer I'm looking at right now be 99% empty space? People just couldn't get a grasp of it. But we think, and Rutherford thought, that his experimental observations verified these conclusions. And with a few alterations, such as how the electrons move around the nucleus and the neutrons in the nucleus, this model of the atom, this nuclear model of the atom, is the same model we employ today. So thank you very much, and I'll see you in the next video.